Find the x values at which function f is not continuous. Determine whether they are removable. In our top function, we have a piecewise function. Natural log of x plus 1 is defined as long as x is greater than or equal to 0. The other piece, 3 minus x squared, it's good for values of x that are less than 0 or negative. Because 0 is my transition number in this function, I'm going to substitute it into both pieces, and if they're defined, it will give us a y value to match the x that we plugged in. Natural log of 0 plus 1 is equal to 0, and so we have a defined point at 0, 0. In the top piece, you're allowed to count x equals 0. Natural log progresses up and right. The other piece, 3 minus x squared, that is a downward opening parabola. If you substitute 0 in for x, 3 minus 0 squared is equal to 3, but we don't count the point because we're not allowed to be equal to 0. That's why there's a hollow point at 0, 3. Downward opening parabola, 3 minus x squared, but only when x's are negative. Because the graph is not continuous at x equals 0, we see that there's a gap between our y values for the same x value. If your answers up here are equal, then you would have a continuous graph. But for this one, we are not continuous at 0 because if we were to draw this diagram, we would have to lift our pencil or pen to get it all drawn. This function is also a piecewise function. Absolute value of x measures the distance that an x value is from 0 on a number line. This top piece, sine of pi over 2x, is defined as long as the absolute value of x is less than 1. That tells us for any value of x between -1 and +1, we can use in that top piece. When the distance from 0 is 1 or larger, then that means you have to have x values that are less than -1 or greater than or equal to +1. Any number in between, and you're back in that top situation. So if these two values of x, -1 and +1, there's a chance our graph may be discontinuous or not continuous. At -1 in our top piece, we have sine of pi over 2 times -1. That's sine of -pi over 2. And if you remember from trig, that's equal to -1. You can also type that into your calculator in radian mode, and it'll give you a -1. The other transition number is +1. Sine of pi over 2 times 1, sine of pi over 2, that's equal to +1. In the other piece, if I substitute -1 in for x, it's just simply equal to -1. If I substitute +1 into x, it's simply +1. -1, when it's an x value, leads to a y value of -1. So here at the bottom left of your screen, this lower left purple dot, that's the coordinates -1, 1. The other number, when x is 1, our value is also 1. This other purple dot has the coordinates 1, 1. Greater than or equal to 1 for x will produce these two rays that are in black. The purple graph in the middle is sine, but it's only between -1 and +1. And technically, I should make those purple dots black because the sine function doesn't get to count them, but the x function, the second piece, does get to count on. That inequality is underlined. So let me write in here that's 1, 1, and then this other point is negative 1, negative 1. You can tell that those two pieces do in fact connect, and so this is a continuous function. The intermediate value theorem, if f of x is continuous on the closed interval a to b, where your function values at those interval endpoints are not the same, k is any number between the two function values, then you've got at least guaranteed one value, they call it c, that's in your interval, such that f of c is equal to k. The diagram to the right, I tried to put it in terms of this theorem. A is an x value. When you plug it into a function, you get a certain value, that's f of a. B is another x value. Plug it into your function, you get another function value. These two function values are different because they're not the same value of y. What intermediate value theorem guarantees is as long as your function is continuous, you can pick a value k that is between f of a and f of b. If you trace it to your graph and go down to the x-axis, that's the value of c that you plug into your function to get an answer of k. Let's look at the example. Explain why the function has at least one zero in the given interval. Our function is f of x equals x cubed plus 6x minus 4. Our interval is 0 to 1. It's a short interval. F of 0 gives us an answer of negative 4. The other endpoint, 1, f of 1, gives us positive 3. One function value is negative, the other function value is positive. With a continuous function, there's no way to get from 0, negative 4 to the point 1, positive 3 without crossing the x-axis. On the x-axis, all your values of y are 0. So I wrote a description underneath, a continuous function passing through 0, negative 4, and I got that point from plugging 0 into my function with an answer of negative 4. And 1, 3, when I plug a 1 in, I get 3 as my answer. Input, output. Must cross the x-axis at least one time. That's what the intermediate value theorem guarantees. Verify that the intermediate value theorem applies to the indicated interval and find the value of c guaranteed by the interval. Guaranteed by the theorem. We have a quadratic function, x squared plus 3x plus 2, an interval of 0 to 5. The graph at the bottom right of your screen, I graphed that particular function from 0 to 5. That's this black arc. F of 0 is equal to 2. F of 0 equals 2. So the point 0, 2 is on the graph. F of 5, the other interval endpoint, gives us an answer of 42. That's an ordered pair of 5, 42. That's a second point on the graph. Those are in blue. 2 and 42 are not equal. 20 is the target number. That's the y value that we were supposed to find. Y value and function value are synonymous. If I trace 20 back over to my function and I go straight to the x-axis, I've got an x value of 3. Now in terms of c and k, 3 is c, 20 is k, because f of 3 is equal to 20. Now, you can't look at a graph and always know there's an exact point just visually. So what I did was I took my function, x squared plus 3x plus 2, and I just set it equal to my target value 20. Subtract 20 on both sides. Factor this trinomial as x plus 6, x minus 3. Set each factor equal to 0, and you'll get x equals negative 6 and x equals positive 3. Since negative 6 is not in our interval of interest, I just lightly crossed it out. Positive 3 is inside the interval 0 to 5, and so that's how I knew my x value would be 3 and my answer would be 20.